com o Raul que estamos todos aqui da banca do Nath.
Ah,
a gente podia tirar uma foto.
claro, é verdade.
Sim,
uma foto
de todos, como se fosse dita,
não é?
Sim.
Verdade. Depois faz uma IA, não? E coloca aí.
É.
Ok. Estamos
15h30? Sim. É no seu relógio, né?
Welcome to this afternoon session. It's my pleasure to introduce the first plenary speaker, Professor Maria Aparecida Rodriguez Hernandez from State University of Maringá. She's going to talk about analytic equivalence of parameterized curves.
Thanks. Well, thank you very much, the organizing committee and scientific committee for this opportunity. It's a great pleasure for me to be here, especially in this so special workshop in honor to Cidinha, our dear Cidinha. Cidinha was my PhD advisor. It was 23 years of collaboration and friendship. And she was so special for me. I only have great memories of Cidinha. She was so generous, especially when we arrive here. And it's very difficult to say something for her. But for me, she was so generous, strong, resilient, and an inspiring woman. And I think she is an inspiration not only for us, but for a new generations of students and especially for women mathematicians. And I think we feel as part of her family. So today I'm talking about joint work with Marcelo Hernandes and Wellington Rocha. We study reducible curves, but now curves in Cn+1. And we take a special parameterization for the curve, the classical Newton-Peirce parameterization. For this is important the concept of semigroup. We study under the action, these objects under the action of the group A. And our purpose in this talk, we present some criteria for eliminating parameters, and eliminating parameters preserving the Newton-Peirce form. And we extend some known results for plane curves. Of course, this work started with Cidinha, also proposed, Cidinha in my thesis, she proposed the study of invariants of parameterized curves in Cn. And we obtain some relations, some inequalities, some formulas relating classical invariants of the theory of curves with classical invariants from singularity theory, like the equidimension, the delta invariant, the multiplicity of the curve, the Turing number, among others. And of course, there is extensive literature in the study of plane curves, especially from the viewpoint of analytic classification. We mention only the works that are directly related with our approach, that the classification, the analytic classification of plane branches obtained by Hefes and Hernandez in 2011, Heaven Hernandez and myself in 2015, and plane curves with several branches of Marcelo and myself in 2024. And with respect to normal forms of curves in Cn, we mentioned Ebay, the works of Ebay. Ebay classifies algebraic curves under particular conditions, including parametrization with invariant delta less than 7. Gibson Hobbs classify asimple parametrized curves in C3. Kohuskin and Sadikov classify stably simple reduced curve singularities in a complex space of any dimension. Dirtominsky classify what he calls fully simple singularities of plane and space curves in the real case with any number of components. And Stevens classifies simple parameterizations in the complex case of arbitrary embedding dimensions. These our main results relate to these. In this talk, we start with a parameterized curve from a map germ given by map germ from C0 to Cn+1, 0 under the action of the group A. With the semigroup, we obtain a Newton parameterization. And the idea is to describe, first we describe deformities in A that preserve this Newton preserved form. And after that, we can describe some criteria for eliminating parameters. We established some notations. C, X, Y denotes the power series ring, the variables X, Y1, Yn, convergent in the neighborhood of the origin. Its maximal ideal is denoted by n+1. And consider F1 of R be the ideal generated by these elements in the maximal ideal. And for us, the local ring associated to the local ring that's given by the quotient of the power series ring over the ideal generated by these elements has crew dimension 1. So the germ of the analytic curve defined by F1, Fr is given by the zero sets of F1, Fr. And we are particularly interested in the parameterization. We study reducible analytic curves parameterized by a map germ phi. So in each context, we have a different equivalence relation. If you have curves given by the zero sets of maps, if you have two curves, C1, C2, we say that these two curves are topologically equivalent. If you have homeomorphisms in the ambient space, U and U prime denotes the neighborhoods of the origin Cn+1, and C1 and C2 are topologically equivalent if phi sends the intersection of here, if you see C1 and C2, okay? So phi sends the intersection of this neighborhood with the curve and the intersection of the other curve with this neighborhood. And if phi is an analytic diffeomorphism, we say that these two curves are analytically equivalent. Correspondingly, when we have parameterizations, if phi1, phi2 are two map germs in these dimensions, so we say that phi1, phi2 are A equivalent if this diagram commutes, if there exist two elements, two pairs of analytic diffeomorphisms in their source in target, so that this diagram commutes. And the relations between these two equivalence relations is that two curves are, it was proven that two curves are analytic equivalent if and only if we have an algebraic translation of this notion. Their local rings are isomorphic, and this correspondence induces an A equivalence between the parameterizations of the corresponding curves. Ebay not used the notation, the language of A equivalence. She used this correspondence with respect to automorphism of power series rings in one variable, that is equivalent to say the diffeomorphism on the source, with automorphism from the power series ring in n+1 variables. So now is equivalent to say an A equivalence relation. For us, we have one hypothesis is that phi is primitive. Primitive means that the components of the curve, the maximum common divisor of the components is 1. Otherwise, if, for example, in this curve, the maximum common divisor is 2. So in this case, we can reparameterize the curve. With this reparameterization, we obtain a primitive parameterization of the semicurve. So our parameterizations are primitive, and an important object associated to the curve is the semigroup, but now we present some main concepts respect to a semigroup of N. Oh. We have this problem. The semigroup N is a general properties. Semigroup is not associated to a curve. So if you have a subset of N that contains zeros, is closed under addition, we call this set is a semigroup. Any semigroup of N is finitely generated. It's possible to obtain a minimal set of generators with the same construction. If you have a semigroup, we start denoting a minimal element in S except 0. There exists this element. So in the after step, we take a minimal element of S except the multiples of V0. And in the other step, we consider the minimal element of S except the obtained by the previous two elements, V0, V1, etc. And with this construction, we prove that Vi is not congruent to Vj mod V0. And moreover, that any and this set is containing any generating set of S, because this, we say that V0, V1, Vg is the minimal generating set of S. And its minimal element, minimal generators, is the multiplicity, is called the multiplicity of the semigroup. So, the complement, the elements in N, except the elements that belong to a semigroup, are called the gaps. For a semigroup can have finite or not number. The number of gaps is finite or not. And these gaps is finite, this number of gaps is finite if and only if these elements satisfy the greatest common divisor is 1. In this case, it's very useful to say that the semigroup is a numerical semigroup. So, of course, if you have a numerical semigroup, if the number of gaps is finite, this means that there exists an element such that C minus 1 not belong to S, and every natural number greater than or equal to the conductor belongs to S. Yes, C is called the conductor. So, the semigroup with a finite number of gaps is very interesting in our study. Okay, now we define a semigroup associated with a curve. We take a primitive parameterization, and a semigroup is defining taking a generic, we take any element in the power series ring, we evaluate with the parameterization, we have a series in T, and you collect all orders of this series. Of course, if this composition is not identically 0. So, so this is an additive semigroup called the value semigroup associated with the curve. And in this case, there exists algorithms that computing the minimal generating set of the semigroup in this work and by Netherlands in 2007. In this example, we have a curve in C4 of multiplicity. Oh, its semigroup is generated by 6, 10, 14, 19, 21. This semigroup has a conductor, 24 is the conductor. So any natural number greater than the conductor belongs to the semigroup. In the complement, the gaps of the semigroup is described by this set. Well, what are relations, some results between for plane curves and curves in Cn plus 1 with n greater than 1? Where for plane curves is well known that the value semigroup is a complete topological invariant. That is, two plane curves are topologically equivalent if and only if their semigroups coincide. For curves in Cn plus 1, we don't have this result. The semigroup is not a topological invariant. In fact, not even the multiplicity of the curve is a topological invariant. But the value semigroup is invariant under A equivalence. This result, for instance, can be given by Gibson-Hobbs in the classification of simple map geometries of curves in C3. So in our case, since our parameterization is primitive, so naturally phi is primitive if and only if phi is a finite determinant. So this is a property that naturally we have when we take a primitive parameterization. Okay, and for us, in some results, it's interesting to consider parameterizations that we call non-degenerate. Degenerate means that with some change of coordinates, some components is identically zero. So in the otherwise, we say that the germ is non-degenerate. And in this case, we say that the embedding dimension of the curve is exactly Cn plus 1. Okay. So now we want to obtain parameterization that we can read in this parameterization some invariants, some concepts that we can look the parameterization and we read some informations. And the classical name, Newton-Puiseux parameterization, that's used for plane curves, we use here to obtain parameterization with the same, when we need to define the following things. But first, we take the components, so general components. Suppose that the minimal order of this series, we permutate the coordinates if necessary to have the minimal order, the first order. It's possible to use some diffeomorphism in the source to prove that this first component is a monomial element. So the order of P1, Pn is greater than or equal to V0. So now we consider some sets that's analogous to this construction. So we denote by gamma 1 the order of elements when we take any series, but we not compose with the parameterization phi. We compose only with the first component of phi, only TV0, we take the other variables equal to 0. Gamma 2, we collect the orders of, we take a series in any plus 1 variable, and we evaluate in the first two components of phi, etc. So it's analogous to this construction. And what is possible to prove? An important remark. Gamma I, that's the notation when we take the order of, we take a series in n plus 1 variables, and we evaluate with the I first components of phi. Phi 0, we do not hear phi 0, sorry. Gamma I is a semigroup, but not necessarily have a conductor. In the first case, this semigroup is generated by V0. Here, I don't know. So it's possible to prove, we prove that any non-degenerate parameterization of an irreducible curve Cn plus 1 with this semigroup is a equivalent to a parameterization given of this form, where here V0 is the minimal element of the semigroup of the curve, W1, Wn satisfy this inequality, and Wy is the minimum element of the semigroup when we eliminate terms, orders that we obtain for the previous I-1 components in gamma I. Well, it's not difficult to prove this result. We start with parameterization. Here, V0 is the minimum element of the components of phi, of the curve, sorry, of my map germ. So we look the first elements in each series. If you have terms with the power are multiples of V0, we eliminate using the first component. We permit, of course, there exists Wy1, such that Wy is an element of the semigroup, but it's not multiple of V0. That exists because we assume that's non-degenerate. And we permutate the components if necessary in order to preserve this order. So now, in the second step, here we denote by W1 this minimal element between these terms. We put in the second component. For the order components now, we analyze the first elements in the key 2, key N2. We have some terms that can be obtained in combining elements in the first and the second component. Yes, we can eliminate. And step by step, we construct the Newton-Puiseux parameterization as given in this form. Satisfying precisely is like to analyze these. We have a minimal element, we take these eliminating these terms. So now using the notation of orders with respect to the curve. So by this result, we can see that all these elements, that's the first elements in each component, belongs to the minimal generating set because the construction proves this. The construction that we obtain is similar. The construction that we obtain, the minimal generating set of the semigroup. So this means that we have here n+1 elements, means with this relation is proof that n+1 is less than or equal to the number of minimal generating set, that's G+1. And it's possible to prove that a semigroup, the maximum number of elements, generators, the minimal generating set is the multiplicity. So this means that the embedding dimension of a curve is less than, of a non-degenerate curve, is less than or equal to this multiplicity. That is, if you have a curve of multiplicity 4, to obtain a curve of multiplicity 4, non-degenerate, we have in C2, C3, and C4. If you have a curve of multiplicity 2 in higher dimensional space, we have some component that is 0. We have a degenerate curve. So, of course, what we have now here is we have a starting point. So our starting point is to have a Newton-Puiseux curve. With this special parameterization, we want to use diffeomorphisms that preserve these initial terms. Because it's important when we want to try to obtain a classification of possible normal forms, necessary to have, we start with this way, and now we want to preserve a certain part, certain elements. So we denote P, V0, W1, Wn, the elements, the Newton-Puiseux parameterizations that start with this. Each component start with V0, TV1, TWN. In this example, we have a parameterized curve in C3, multiplicity 3. And here we have T7 in any element here greater than 7. and we put W2 trying to obtain all possible Newton-Puiseux parameterizations starting with T3, T7. So W2 need to be greater than 7, and with the property that W2 not belong to the semigroup obtained by the first two components. In this case, this semigroup obtained by the first two components is generated by 3 and 7. In this case, the semigroup has a conductor, and the conductor is 12. So W2 is a gap of not belong to this semigroup, not belong to the semigroup obtained by the first component. So we have only two possibilities, because W2 is greater than 7. So the possibilities is 8 and 11. So T8 and T11 are the possible Newton-Puiseux parameterization starting with T3, T7. Okay, how? Now, the next step is to characterize the diffeomorphisms of the group A that preserve the Newton-Puiseux form. So here, if we have a Newton-Puiseux parameterization, the diffeomorphism in the A group preserving this Newton-Puiseux form is given to this way, where epsilon is a non-zero complex number. 80, 81, 8i are elements that belongs to this, the ideal generated by yk plus 1 yn plus the maximal square. With this property, we obtain that the order of this element is greater than wk. This means that we preserve the initial terms. And note that here, the source diffeomorphism and target diffeomorphism, 80 appear in these two diffeomorphisms. Okay. So the set of these diffeomorphisms is not a subgroup of the A group. So we consider subgroups of the group A that contains the previous diffeomorphisms. So we denote A1 tilde, the subgroup of A. In that case, this means to take epsilon equal to 1. That is given, the one jet of this diffeomorphism is the identity of rho. Sigma is given to this way. And this meaning that the Jacobian matrix of sigma at the origin is unipotent upper triangular. And 8 denote the subgroup of homotheties of A. So the previous diffeomorphism is a composition of an element in 8 and an element of A1 tilde. So, but the homotheties neither introduce nor eliminate terms in the parameterization, so we focus now on the A1 tilde action. Okay, we put my parameterization in a Newton-Puiseux parameterization, and we take rho and sigma like before, because we know that these diffeomorphisms preserve the Newton-Puiseux form. When we apply, when we see the action of this diffeomorphism in phi, what's happened? What's happened that we obtain phi, and we add in each component. In the first component, TV0, we preserve this element. But in the second, but the other components, we add these terms. That is, when we apply the diffeomorphism, we know we describe the action of this diffeomorphism in a parameterization. We have here 8i, that's the elements that appear in diffeomorphism appear here. And what yi prime means the derivative of the yi component quotient with the derivative of the first component. What we have here is that when we choose, if you take 8, 0, 0, and we choose 8i, it's interesting because 8i appear only in theta i. So we are changing only the I plus 1 component. But the problem is when you take 8, 0, appear this element in the other n components. So, what's happened if you want to eliminate one term? Suppose we have a parameterization given to this way. We have in the YY component, and we want to eliminate a term of order K. We need to, well, if you have in this component theta I, given as before, of this order, we can take, there exists H0, Hi, such that this order, we adjust the coefficient of theta I to eliminate this term. The problem is what this action do with the other components. So, these are some eliminating criteria that is a generalization of classical eliminating criteria for plane branches, for plane curves. The first point is eliminate terms in which K belong to the semigroup is perfect. Because if K belong to the semigroup, we eliminate this term in the component Yi. In this component, we preserve the K minus 1 jet, and we add possibly new terms greater than K in this component. But in the other components, we preserve. It's perfect. We eliminate terms because here, when you look the definition of theta I, we take, if K is order of the semigroup, we take 8, 0, 0, so we don't have these terms. And 8i, we take, there exists the 8i, so that this order is exactly the element of the semigroup. And it's good because in the other components, we don't have the influence of, we don't add nothing, so perfect. And look that the problem of this expression, we forgot to say. The problem of this expression is that I don't know if the order of theta I comes from this initial part or comes from this sum. This is the problem. We do not have control of this. So, any element of the semigroup, if you have an element, K is order of element of the semigroup, we can eliminate these terms, preserving the other components, and not preserving the K minus 1 jet and adding something, eventually some terms greater than K. But with the other part here, the order of this, when we evaluate this order, we have an element of the semigroup plus WY minus V0. So we can eliminate one term given by, and that belongs to the semigroup plus WY minus V0. What's happening in the other components? In the other components, it depends. For the components greater than I, in the other components greater than I, we preserve a certain jet. But the previous components, we can introduce other terms. So it's necessary to take care to use this kind of elimination. So the classical, this elimination of terms of the semigroup in terms of gamma plus V1 minus V0 is a classical result in the theory of plane curves. Zariski and Ebay obtaining this original result for reducible curves. Zariski calls this parameterization a short parameterization. And in our case, to obtain a generalization of this result and to obtain something that's not change the previous components, our theorem is that any non-degenerate parameterization with this semigroup, as in the plane curves, as in the same case of plane curves, we have a Newton-Peirson parameterization in which in this component, we eliminate any power that belongs to the semigroup union element of the semigroup plus V1. V1 is W1. V1 minus V0. In the other components, we eliminate elements of the semigroup. Because if we eliminate here elements in gamma plus W2 minus V0, we can reintroduce terms in the first component. As a natural consequence of the previous result is that we can obtain a polynomial parameterization because the semigroup, our semigroup has a conductor. So any element greater the conductor belongs to the semigroup, and we eliminate all terms of the semigroup. It's necessary to use other concepts that we not define here, the conductor ideal, etc. But we truncate, it's possible to truncate in the following, we analyze Wi and the conductor. If the conductor minus 1 is less than Wi, you truncate in Wi. But if the conductor minus 1 is the maximum, the truncation is conductor minus 1. So we analyze the second, the third component. We take this term AI, and phi is the equivalent to E jet of phi, where E is the maximum of A1, AN. For example, in this class that we analyzed before, W2 is 8R11. The conductor is W2 minus 2. So when we take W2, 8, the conductor is 6. 6 is less than this first element. So the truncation here is in 7. Of course, in the other component. So here, this curve is a equivalent to a monomial parameterization. So when W2 is 11, W2 minus 2 is 9. So here we have T8 and some coefficient with T8. The truncation is in 8, and the other component we truncate in 11 for some A in A. And observe that this parameterization, here, the parameterization, the second, when W2 is 11, we have a parameterization precisely given to this way, because 8 is not an element in the semigroup generated by 3 and 7 and 11, and is easy to see that is can be not be given as an element in gamma plus V1 minus V0. So we have a parameterization like in short parameterization of Zariski. And we can generalize, in this case, W2 equal to 8, we can generalize. There we have a curve of multiplicity 3 in C3. Here we have a parameterization of multiplicity M in CM. Here, a Newton-Piso parameterization. The semigroup is in this case generated by the first elements. The conductor in this case is the maximum generator of gamma minus the multiplicity plus 1. And if W1 is greater than the conductor, this parameterization is equivalent to a monomial parameterization. What we obtain until now is that the criteria to eliminate terms in gamma, terms of gamma plus Wi minus V0 take care with this elimination. And it's possible, is also possible to prove, we not show the details here, but we can eliminate if you are in a component yi, and we want to eliminate one term here. Any element that is given by k plus multiples of V0, we can eliminate. Of course, we use this when we apply this result, we use this elimination criteria, but it's necessary to take care in the order components. Well, other result that is possible to generalize, that's classical in theory of curves, is an invariant that Zariski, it's called after that, was studied by Zariski, and he's defined the following form. It's necessary to consider a parameterization given of this form. It is important. If you have a parameterization like this, take lambda, if there exists, if phi is not monomial, there exists and a power here the minimal element that not belong to the semigroup union gamma plus V1 minus V0 such that this coefficient is different to 0. This number is an invariant under A equivalence. So, and if our semigroup of the curve has at least 3 generators, these invariants satisfy this property. Lambda is less than the third invariant, the third generator of the semigroup. What happened in our case, in a curve in Cn plus 1? Well, take the same kind of parameterization given to this way, and we define precisely as Zariski says. Zariski is defined. Take lambda, the minimal element in this kind of parameterization satisfying the same property. This coefficient non-zero is the minimal element that appear here. But here, we need to impose the condition that lambda is less than V2 because it is not true in general. And we need this hypothesis. If this number is less than the third invariant of the third generator of gamma, the lambda is invariant with respect to the diffeomorphism that we consider here, that diffeomorphism that preserve the need to preserve form. Otherwise, this is not true. In this example, we have the parameterization as in short parameterization of Zariski. And if A is different to 0, 8 is the invariant. But if you take this curve in C4, multiplicity 9, the candidate of lambda will be 32, but the semigroup is generated by 9, 12, 19, and 22. And lambda is greater than 19, that's the third generator of the semigroup. In this case, we eliminate 32. Taking epsilon H0, H1 as follows. We analyze the order of the theta 1 that we defined before, and we can eliminate these terms. So, and we said, we present some result using the A1 tilde action and the homotity. Homotity is used to normalize some coefficients. For instance, if you have the invariant lambda, we can normalize this coefficient, like in this case. In this case, using our results, we obtain the classification of multiplicity 3, for instance, multiplicity 3 in C3 of Gibbs and Hobbes. That's given to this way. And in this case, this power is precisely the invariant lambda. Observe that lambda is less than V2. V2 minus 3K. So these are normal forms that we obtain using this previous result. And what we have is we apply our results to obtain the normal forms of non-degenerate parametrized curves of multiplicity 4 in C3. We not present here, but we obtain the curves of multiplicity 4 in C4 using, by hand, a lot of computations, but we apply these results and other results that we not present here, and we obtain the normal forms for this class of curves of multiplicity 4. Finishing the possible classification, because the classification of simple map germs of curves in C3 contain curves of multiplicity 2, 3, and some of multiplicity 4. But here we finish the classification of multiplicity 4 in C3 and in C4. So I think, thank you very much. I finish here for our beloved Cidinha. Thank you very much.
Okay, thank you, Lenise, for a nice talk. Are there any questions or comments? Yes?
Hi, thank you for the talk. So my question was, can you obtain some other elimination criteria if you assume that some of the generators of the semigroup are differential values of the previous one? Like, for example, if you start with two comprised numbers, then the new generator needs to be like differential forms of the previous one.
That's the here. Well, we not take the exactly as you said, the differentials, because differentials appear here. No, we not to use the same definition, the order of one forms of the previous components, but can be interesting to analyze. What we have is we apply, for example, in the classification of curves of multiplicity 4, we use the algorithm of Marcelo and Abramo Hefes for the whole model of differentials, but including this case of the multiplicity is not so big, we have a problem because in some cases, the order of the differential is not the order of the time. The order is given by this element. And the problem is not to have, what's the problem to not generalize what we have for plane curves? Because for plane curves, this part control the order of the elements that we include in each component, in only one component. But here we don't have the same result. We don't have an invariant now, until now, that reads what happened when you evaluate this order. We know all gaps that appear in the parameterization is given by the order of which structure, which algebraic structure gives the order of theta I. It's what we need. Perhaps to analyze some idea that you said can be interesting.
Okay, thank you.
Anything else? Yes. Here.
Hi. Is there a characterizations of parameterized curves which are A equivalent to a monomial parameterization?
L equivalent.
A equivalent. I mean, in page 36, you discussed something like this, but I don't know if it's if and only if.
Yes, no, only if. In the case of multiplicity MCM, no?
Yeah, there
we have a monomial
is,
parameterization. But you want to know if you have a hypothesis that we put before in order to have A equivalent to a monomial.
Exactly.
For plane curves, we have, because we have an invariant, analytic invariant that orders of differentials. You want this order on this set is empty, if and only if the parameterization is monomial. In this case, you not analyze if, because we don't have this invariant, because the invariant, we have the semigroup, and we can take differentials given by g dx plus 8 dy. We compose phi with the parameterization. That's the same, the compose here, the components, the dx, the derivative of the first component of phi, etc., is the other notation, but we put here x prime t plus 8 phi y prime. When we take this order minus the multiplicity is an invariant. The order of these elements minus the multiplicity is an invariant. And when this invariant contains the semigroup, the set contains the semigroup except the 0. And when we take the orders of lambda except the semigroup, if is empty, if and only if phi is monomial. It's interesting to have something here, but I don't know which property characterized in this case.
Okay, thank you.
Okay. Yes. Daniel?
Thank you, Elenise, for this very nice talk. So my question is about this slide. When you take a projection, a plane projection in C2 of this curve, the numbers m double one double m minus one are the characteristic exponents of the plane curve, the projected plane curve. Is there some relation about the topology of generic plane curves?
Because the problem is the semigroup is not invariant. There's a topological invariant.
Topological
I don't
invariant.
know if I projective, if you have some relation with respect to the characteristic exponent, because when you have a parameterization of a plane curve, the characteristic exponent appear in the parameterization.
Appear in the parameterization.
But
Okay.
the generators of the semigroup, not all generators. There is a relation between.
Okay.
There is given a characteristic exponents, we obtain the
They can be
generators and
different.
vice versa. Yes,
Okay.
but not necessarily appear. Here, we don't have all generators of the semigroup. M, W1, Wm minus 1 belongs to the minimal set of generators, but we can have more.
Okay, so in a precise way, we can say that the characteristic exponents can be given in terms of these numbers, right? The characteristic exponents of the projection, plane projection. I don't know.
Yes, perhaps, I don't know.
Okay, thank you.
Need to
Thank you very
analyze
much.
this. Thank you for this question.
I have one question. So for space curves, there is a generalization of the Milnor number that was done by Bushbach-Growell. So it's possible to read this Milnor number in terms of your exponents or semigroup or?
It's interesting to analyze, but I
Because
don't know.
The Milnor number is twice the delta invariant.
For
Is it
plane
related?
curves, yes.
And also for space curves is the same.
There is a lot of relations proved by Grow and other for curves in general, including reduced curves. But I don't remember precisely because it involves other invariants. But I think there is something for Milnor number.
The Milnor's formula is exactly the same. So mu equal to delta plus r minus 1. So in the case that you have only one branch, it's twice. Milnor
It's
is
twice.
the delta.
Yes.
Okay.
Yes.
Okay. So thank you.
Thank you.
Anything else? So let's thank the speaker again. Okay, so let's start the last talk of this afternoon session. It's my pleasure to introduce this very special and perhaps the most important talk of the workshop that will be by my colleague Raúl Oset Sinha from University of Valencia and Thais Maria Dalbelo from the UFSCar, and will be about Cidinha's mathematical legacy.
Is it working? Yeah, okay. So thank you very much, Juanjo. We will take turns, Thais and me. Okay, I will start first. This is a very difficult talk in so many different aspects. Obviously, the emotional aspect, what Cidinha meant to practically everyone here. And also because of the amount of work she did in her life. So it's quite difficult, but we'll try. Let's see. So this is the sketch of the talk. We'll talk a little bit about Cidinha, both Thais and me, and then we will talk about her work. So to start with, I wanted to say what was Cidinha to me, and we met for first time in 2006. It was the first time I came to São Carlos to the workshop. And of course, I was coming with my supervisor, but Carmen Romero Fuster, but she couldn't come in the end, so I came on my own. And Cidinha welcomed me like she used to welcome everyone. And then in 2008, during my PhD, I did a 2-month visit in which I could discuss mathematics with her. But our collaboration really started in 2010. That's when I did my postdoc with her. I did a 3-year postdoc with her. And since then, we didn't stop collaborating. In fact, I became her closest collaborator in the past 20 years. And this is something that's always surprised me a lot, because I started working with Cidinha when she was 62 years old. And I became her closest collaborator since then. This is very, very rare. Most people at 62 are starting to retire. And you never know, you can still meet your closest collaborator. In fact, I still have 2 preprints with her, which once they are published, I will become the closest collaborator, absolutely. But anyways, I consider her my second supervisor. As I said, my PhD supervisor was Carmen Romero Fuster, but I consider Cidinha my second supervisor because she introduced me into so many different subjects, and I think she was my mentor and obviously a friend. She was generous, helpful, tireless. You all know, we've been hearing during this week so many people talking about Cidinha. And she touched virtually every subject in singularity theory. So the goal of this talk is, if any, maybe not explain so much the mathematics, but to show the wideness, the diversity, and the reach of her mathematical legacy. And this is a very difficult task, because we will see later. But anyways, so there is a saying in Spain, and maybe in your country you have something similar, that says that behind every great man, there is a great woman. I think in this case, we should say it's upside down. Behind every great woman, there is a great man. So I would like to dedicate this talk to Gaspar, because without his support and constant support, most of this work would have not been possible. Okay, so in a lighter note, this is what Cidinha's typical workday looked like. So from 8 to 10, she had maybe a PhD student. She was discussing on some subject. And then from 10 to 12, she had another meeting on a completely different subject. And then there was lunch. Then from 2 to 4, maybe a visiting professor. And from 4 to 6, maybe another postdoc, another visiting professor, in completely different subjects. And if you were in any of these meetings, you were completely exhausted after 2 hours. But she had 4 of these per day. How could she manage this? Coffee. There was coffee. And also in the afternoon, she used to rest. And she used to go for Pilates or choir or piano in the last years. So, but this is the way in which she managed to do so much work. But if you're a close collaborator of her, you knew that she even worked before breakfast and after supper, because I have received emails from Cidinha at 6 o'clock in the morning and at 11 o'clock at night. So this was her typical work day. And here we have Masainet. This is of a couple of months ago. There were 92 publications, but today I looked and it's already 94. And citations have gone up to 800. And in fact, as I said, I know I have 2 preprints, and I know some other people have preprints with Cidinha, so I've calculated that this will reach 100. And she had 76 co-authors. 76 co-authors. That is a lot. And so many papers. So imagine the difficult task of giving this talk about her mathematical legacy. But anyways, and I checked this morning in Central Blood, and there it says the co-authors. I think it was 995. So there are like 76 with Cidinha number 1 and almost 1,000 with Cidinha number 2. And I wanted to, because in Cidinha's 70th birthday, I gave a talk about her work also. In fact, I'm recycling some of the stuff, but not much. And I wanted to point out at this. She had this, she was 70 years old, 61 papers, 92 in 7 years, 30 papers in 7 years, more than 30. That is like, Cidinha, what the... Anyways, so yeah, this is quite impressive. I mean, someone over 70 with this production and this capacity of doing mathematics. Anyways, so we've tried to separate her work in different areas. I think the main areas are the following. So obviously, singularities of mappings. This was her favorite subject. And it's what she worked throughout all her life, from her thesis to the end. And then generic geometry, which she also worked all throughout her life, and it's actually her most cited area. Then in the last 25 years, she worked in ellipsis geometry. She also worked in the determinantal singularities, topology of singularities, like Miller fibration, things like that. And then some smaller areas where she didn't work that much, but that she also has some contributions, some PhD students, like Thais will show you in a moment, like bifurcation theory, dynamical systems, or real algebraic geometry. So I will talk about the first 3 subjects, which are the subjects in which I collaborated with her, and Thais will talk about the last 3. Okay? So now, please, Thais.
Good afternoon, everyone. I met Professor Cidinha in 29 when I started my master here at ICMC. And since then, she became an example of resilience and determination for me. And she was also a supportive shoulder, genuine north, a motivated mentor who helped me build connections. And I had the great pleasure of work with Professor Cidinha. And as a collaborator, she was brilliant, humble, lovely, cheerful, and incredibly fun. She was, as we saw in Ellen's talk yesterday, and in the beautiful story that she shared with us, Cidinha always had an attentive eye for young mathematicians, right? And for the students too. She was also patient and always willing to listen. I think that this is not the the last version, but okay. And because of this, she was a genuine leader. As Raul told, it is impossible to talk about Cidinha without mentioning her incredible partner, Professor Gaspar. And the way that I choose to show you how incredible Gaspar was in helping and supporting her is sharing with you two stories that, in my opinion, are really lovely. So, while finishing my master's in São José do Rio Preto, a very hot city, I traveled over 3 hours by bus to São Carlos to discuss a PhD with Professor Cidinha. One year that São Carlos is famous for its unpredictable weather, I did bring a jacket. I arrived in the middle of cold rain, shivering, and knowing no one at ICMC. When I reached Professor Cidinha's office, she welcomed me with great kindness and immediately noticed I was cold. She instantly called Professor Gaspar, asking him to bring one of her jackets. Less than 50 minutes later, Professor Gaspar arrived with a coat for me to wear. This is Professor Miriam Pereira. Now she is professor at Federal University of Paraíba. She also has a PhD student now, and he is here attending the conference. In the summer school of 2023, I came to São Carlos to study with Professor Cidinha on the project entitled Curves and Singularities. I remember the first time I met her in her office. She was incredible, attentive, and warm. She explained what we would be studying, lent me the book we would use, and made sure I was well settled in the city and had everything I needed. A few days went by, and I fell down one of their staircases at ICMC. I ended up hurting my foot and couldn't walk. Professor Cidinha was more concerned about me and my well-being than about the progress of the project. She lent me her own wheelchair so I could move around ICMC and attend the summer classes. Sometimes after the seminar, she would ask Professor Gaspar to drive me back to USP housing where I was staying. Often, her little grandson was with them. This is Odete Lara. On that moment, she was an undergraduate student. Now she's a PhD student at UFSCar, and she's here helping us in organizing the conference. We can't forget to talk about the workshop, this conference that she carries so deeply. The first workshop in real and complex singularities was organized by Professor Leubel, the second by Cidinha, and the third was organized by Tom Arar. And it was when the word international was added to the name. Cidinha was always involved with the other members of the São Carlos Singularity group and was the driving force in maintaining the workshop alive. Even during the pandemic, in 2020, we had the pandemic, and we would like to organize the workshop, and we didn't know how. It was everything new for everyone, and after long discussions, we decided to do a online conference, and the coordinators on that year was Professor Miriam Manuel and Professor Alex. And we, as I told you, we didn't, nobody knows what to do, how to do, and we did a lot of online meetings by Gemeet, many of them late at night, and Cidinha was there in all of them. She was there with us. Cidinha, as I told you, she was a genuine leader because of all of this. She was a genuine leader. And we can't not mention the students, right? Working with the students is one of the things that she most liked. And she had a lot of students. Here we have these names. Many of them are here in the conference. Here are 11, but there are more. In fact, she had 23 students, a lot, right? And she also had postdocs. Here we have some of them. Raul is one of them, but there are more. In the total, she had 22 postdocs. And there was more, right? She had many students, of master students and also undergraduate students. And one of the things that Cidinha also loved was to interacting with the students, to work in some new topic that she was interested in. And as Raul told, she worked in many areas of singularity theory, including with the students and the postdocs. For instance, singularities of mappings, generic geometry, by Lipschitz geometry, determinantal singularities, topology of singularities, bifurcation theory, dynamical system, and the real algebraic geometry. And she won many important prizes. She was member of the Brazilian Academy of Science. She was awarded the National Order of Scientific Merit, award which is presented by the President of the Republic of Brazil. She was honorary member of the Brazilian Mathematical Society. She was elected fellow of the World Academy of Science since January of the last year. She was also awarded the Mathematical Leadership in Latin America award by the Institute of Mathematical Science of Americas. And she also won America's Prize, which was also by the Institute of Mathematical Science of America. Unfortunately, when this last prize was presented, she had already passed, but her daughter, Juliana, was there on behalf of her.
Okay, so let's get to work. Cidinha's thesis it started with Gaffney in the US, but there were some complications over there, and she came back, and Luis Antonio Favaro continued, and she defended her thesis in 1983 about CL determina sau finita e aplica SOEs. There was a paper out of this, which is actually her first paper. And lots of work from this thesis was not published. So, for example, there's this result. First of all, you say that a germ, if you consider the map germ from Cn to or Kn to Kp, you say that the A orbit is open in the K orbit if the tangent spaces coincide. Okay. So, spoiler alert. This is the only theorem I'm going to show we are going to show in the whole talk. Okay. Good for you, I believe. But so I chose the theorem. It's from her thesis. It wasn't published, and she was very fond of this theorem. And it's a characterization of when the orbit is open in the K orbit. And I chose this theorem also because it's the way in which she understood singularities of mappings. She always thought of how the orbits the A orbits were inside the K orbits. And why is this relevant? This is relevant because, for example, if you have a K orbit where there is no open A orbit, then this means that you're going to have modality. Okay, there is not simple. And if a non-stable germ has the A orbit open in the K orbit, then this means that there is no stable unfolding before the Berzon unfolding. Okay, this is quite relevant in the theory of singularities. And from this theorem, in her thesis, it was implicit, that it wasn't even stated, but in her thesis, it was implicit that a pair of dimensions, MP, is in the nice dimensions if and only if the A codimension 1 germs are simple. If you're an expert in the field, the only if part is more or less doable. It's the if part that was in her thesis. And I also chose this for another reason. The other reason is that I have the proof. And this is a proof from original notes from Cidinha. I think it's from the 80s, yeah? And this is a more modern notes of that same proof. And I want to show here, Cidinha did everything by hand. She did matrices 20 by 20 and did all the calculations by hand. Fortunately, some of her newer collaborators learned how to use Singular and things, but she continued doing the calculations by hand, and she has some notes with some matrices. I have loads of notes that she sent to me with calculations that are just crazy. But anyways, so the first years, there was the Solange-Mancini's thesis, which I believe was the first, if not either her or Marcelo. And in Solange-Mancini's thesis, they worked on phi equivalence, which was an equivalence that had been defined earlier by Favaro and Mendes. And it's basically an equivalence between map germs, which preserves the fibers of another map. But the important thing is that it has applications to many different subjects, like divergent diagrams, foliations, and more recently to unfoldings or augmentations. And here are 3 papers that came out from that thesis or collaboration, actually. And one of them is with Carmen Fuster and obviously with Solange-Mancini and with Marco Teixeira, this one. And then, more or less in the same period, was Marcelo Saya's thesis, where they studied Whitney equisingularity of the formations of hypersurfaces using the Newton polyhedron. This is something that has been, since then, there has been lots of work in this line since then. And they also studied, continuing Cidinha's thesis, CL determinacy of map germs. Here are papers with Marcelo, and one of them was together with Bruce also. So then came the collaboration with Rieger, one of her most fruitful collaborations. Rieger had just classified the map germs from the plane to the plane, simple map germs from the plane to the plane, and they continued his classification. But what was important of this continuation was that they classified corank 2 simple germs from Kn to K2. And this, I believe, is probably one of the first classifications in corank 2. Singularities. Up to then, all the classifications were of simple corank 1. So this was important. They also defined the concept of M deformations, which is when you have a real map germ and there exists a deformation which has all the zero-stable singularities that you can calculate in the complexification. Okay, this is related to good real pictures, which Mond and other people have studied. In fact, good real pictures implied M deformations. So these are the papers with Joachim Rieger. Two of them are also with Roberta Vicatic. Then came Tomasella's thesis. In Tomasella's thesis, they studied Rx equivalence. So you have function germs, and usually the group that acts is diffeomorphisms in the source. This is called the group R. But when there's a certain submanifold in the source which you have to preserve, then you only want these diffeomorphisms in the source which preserve this submanifold. And this is what is called Rx equivalence. So they gave sufficient conditions for topological triviality of such maps. In fact, it's an infinitesimal criterion, and they studied certain invariants. So this was done. These conditions for topological triviality were very important at the time, and she took it to the context of Rx equivalence. Here are the papers with Joao Tomasella, and one of them is also together with Imran Ahmed. Following this line, but much more recent, is her collaboration with Carles Vivia Osina and Konstantinos Kourliouros, because they also studied functions and on a certain singular manifold X. And in fact, what they did very recently was characterize quasi-homogeneity of the pair X. You have a function on a singular variety X. And they proved a Saito type theorem. So, you know, for functions, you have the Saito proved that if the Milnor number and the Turino number are equal, then the map is quasi-homogeneous. So they proved the same, but in the relative version. So there is a version of the relative Milnor number, which is called the Bruce-Roberts Milnor number, and the relative Turino number. And they proved that equality implies quasi-homogeneity of the pair. Here are papers, first one only with Carles, and the second one, the three of them. The second and third, the three of them. Then comes the collaboration with me and with Roberta Vicatic. So what we did, continuing some open problems for my thesis, we classified all codimension 2 multi-germs. So when you have a map germ, you can consider different branches, and then you have a multi-germ. And obviously, classification of multi-germs gets a bit more complicated. There had been a classification of A codimension 1 multi-germs, and we did for A codimension 2 in any pairs of dimensions, MP. And we studied also simplicity, and together with Takashi Nishimura, we gave a method to compute liftable vector fields, which are very closely related, or basically the same as what many people call the der log, the logarithmic derivations. And we defined the extra nice dimensions. This, I believe, is my best paper with her. We were very happy with this paper. In this paper, we defined a refinement of the nice dimensions, and this is where stable one-parameter families are dense. So one-parameter families which only at a finite number of points cross codimension 1 singularities. And these are also characterized as where the pairs of dimensions where all stable maps admit an A codimension 1 hyperplane section, and also characterized by the pairs of dimensions where all A codimension 2 germs are simple. I remember when we were working on this paper, and when we discovered the characterization, because we started with this goal, but then when we realized that it was equivalent to where stable one-parameter families were dense, Cidinha suddenly said, "We'll publish it in Annals." And well, not exactly, kind of Annalen, mathematician Annalen. It wasn't Annals, but it was okay. And related to this subject, she recently collaborated in the handbook of singularities, the handbook in volume 3. There are 8 volumes, I think, now, or something like that. And she wrote this very long, 80 pages, very long paper survey on all the new results on density of stable mappings. Also, Maria Lenice just gave a talk, and she mentioned, I think, this work with Cidinha. She worked in finite determinacy of monomial map germs from, there should be a comma 0 here, from C2 to C4, and they defined also a join operation. A couple of papers here, one of them quite recent. And also with Farnik and Jelonek, they studied finite determinacy and zero stable invariance of global maps. Okay, when you study germs is one thing. When you study global maps, things are much more complicated. And they have a couple of papers on this subject. Okay, so of course, Whitney equisingularity was a subject that was always present in Cidinha's research. And basically, I'm not giving the proper definition, but when you have a family of map germs, and it can be in any partial dimensions, but well, C2, C3 is the case that has been studied. And when you have a family or unfolding, it's called Whitney equisingular. If it is a stratified map in a certain sense, Tom sense. But when, in any case, what's important, Whitney equisingularity implies topological triviality, okay? So Gaffney proved that Whitney equisingular is equivalent to constancy of the Miller numbers of certain double point spaces and multiplicities and certain multiplicities. So Cidinha conjectured that the constancy of the Miller number of the double point set implied Whitney equisingular, which, using results by Bobadilla and Pereira, this is the converse. This means that topological triviality implies Whitney equisingular. So for a very long time, she tried to prove this until counterexample. They found a counterexample together with Otoniel Silva, and this was published in this paper over here. And in fact, we have here Aldicio Miranda. He has a 3D printer, and he did this very, very nice 3D print of this surface, which Otoniel called the Ruas surface. Okay, in fact, can I say? Yeah. We have a surprise. Aldicio has printed some small replicas of this surface, and there will be it as a present for all registered participants. At the end of the talk, you can pick up your copy of the Ruas surface. It comes even with the parametrization. So this was the counterexample. And from each of the subjects, we decided to get some comments from collaborators in that subject. My criteria was collaborators who had at least 3 papers with Cidinha. So don't feel, if I didn't contact you, please don't feel bad. So Solange, she said, I met Cidinha during my undergraduate studies and shared more than 5 decades of friendship and academic life with her. I remember that Cidinha always had a serene, organized, and impeccable demeanor. I also got some very nice words from João Tomasella. It was a privilege and a joy to share part of my academic journey with Cidinha. To me, she was much more than an advisor and collaborator. She was my academic mother and a fundamental presence in my development, both professionally and personally. I will always cherish the memory of her perfume in the department hallways and the coffee breaks that would arise whenever we were tired, out of ideas, or when I was facing personal difficulties. In those conversations, she always lifted my spirits and helped me return to work with renewed enthusiasm. Beyond being a brilliant scientist, I will remember her as a deeply kind and inspiring person. She will be greatly missed, but her legacy will live on in all of those who had the privilege of knowing and working with her. I also have some words from Carles Vivia. Cidinha has been a reference from many points of view, the most important on a human level, always attentive, available, optimistic, and elegant. We all know that research in mathematics can go through stages in which it seems that the topic in question is impenetrable, but collaborating with Cidinha made everything lighter. There was always an implicit positivity and enthusiasm that in one way or another meant that we would not lose sight of the topic. I think we have all learned a lot from her way of approaching research and the broad vision she had of the various topics related to singularities. I have always been able to count on her help and guidance. She was interested in how things were going in our tasks, and of course, I will always be grateful to her for having been part of my jury of my thesis. Also, Maria Lenice sent some words, some of which also appeared in her talk earlier before. Cidinha possessed extensive mathematical knowledge in various fields and was always concerned with the quality of the articles she produced. She had a great ability to bring people together through events and collaborative projects that always involved several universities in Brazil and abroad. With her leadership spirit and her kindness, she was a strong woman of great courage, respected in Brazil and abroad, who inspires us. And I also have an anecdote shared by Takashi Nishimura. He said, I was staying at ICMC for about 3 weeks from mid-January to early February 2014. A big international conference on partial differential equation was being held, and luckily I was there at the time. Cidinha said, in Brazil, Artur Avila and Fernando Codá Marques are candidates for the Fields Medal of this year. I prefer Codá. Today Codá is giving a lecture later in this conference, so let's go and listen together. I hesitated, saying, but I haven't paid the registration fee for the international conference. She said, it's okay, no problem, you can come. So we went together, and when the lecture ended, I glanced over at Cidinha, and she was already gone. A little while later, she came back and said, I went to talk to Codá. Apparently, Codá lived in São Carlos when he was little because of his father's job. So I feel an even stronger connection to him now. I was once again struck by Cidinha's outstanding communication skills. Okay, so we change subject, and now we start with generic geometry. And here is when we cannot not mention Carmen Romero Fuster. Carmen lived here in São Carlos for some time, and they started their collaboration by co-supervising Dirce Mochida's thesis. They studied surfaces in R4 from a singularity theory viewpoint. They studied the curvature parabola, inflection points, asymptotic directions, and some global results too. And in fact, the work that came from this thesis could be considered in a way the foundations of generic geometry of submanifolds, at least from the singularity theory point of view. In fact, these are some of her most cited papers. Some of them have up to 70 citations, and there's also one with Ronaldo Garcia here. So this was a very good collaboration with Carmen and Dirce, of course. And then Farid Tari and Suichi Izumilla joined the game. Still with Carmen Romero Fuster and Farid, they characterized asymptotic directions in R5 in terms of contact with K-planes for any K. It's a very nice paper. And they also studied, only with Farid, studied lines of principal curvature for surfaces in R5. There's these two papers. The first one is of the three of them. The second one is only with Farid. And also Izumilla, she joined Izumilla's long-time project of generic geometry of submanifolds in hyperbolic space, de Sitter space, etc. And through a co-supervision of Marcelo Buosi. This was something that Cidinha used to do. Whenever someone came to São Carlos, it was completely obligatory that they went to Cidinha's office to discuss mathematics. Cidinha wanted to know what everyone was doing. And in this way, she got to collaborate with so many people. So she joined Izumilla with this co-supervised thesis, and there were a couple of papers here. And we've talked about Carmen, Farid, Izumilla, and Cidinha. And here comes the book that the four of them wrote together, Differential Geometry from a Singularity Theory Viewpoint. And this is the Bible of generic geometry nowadays. So they have the generic geometry of non-singular submanifolds in Euclidean spaces, and includes the basics on geometry, singularity theory, contact, Lagrangian and Legendrian singularities. They study surfaces in R3, R4, R5, and space-like surfaces in Minkowski space. And this serves as a guide to study geometry of singular objects, which is what nowadays is being also a very wide area of research. So also in non-Euclidean geometries, with Ana Claudia Navarro and Masaki Kasedo, they studied second-order geometry of space-like surfaces in the Sitter space. We have a couple of papers. And in the context of line congruences, they classified singularities in the equiaffine framework. This was from Igor Chagas Santos' thesis. very, very recent. I think one of the last theses. And in these collaborations, together with Deborah Lopez and with Tito Tina Medina Tejeda, which was also another PhD student of Cidinha. And then comes also the collaboration with Janesco. Through Janesco, she collaborated with the Polish School of Singularities, and they studied things like symmetry defects, affine equidistance, and also surfaces in R4. Papers with also Jelonek, with Wojtek Domirc and Pedro Rios, and Jelonek, and even with Giblin also. All these papers are with Janesco and those other people. So then, as I said, you have the Euclidean setting, the regular submanifolds in the Euclidean spaces, but then you have singular submanifolds. And in the setting of singular submanifolds, together with me, we co-supervised the thesis of Pedro Benedini Riul, and we studied, as I said, singular submanifolds. In particular, corank-1 surfaces in R4. We studied the curvature parabola, which had been defined by Martins and Nuño Ballestero, but in this context. And then the types of curvature lossy that can appear in corank-1 three manifolds in R5. There were here three papers, one of them with Andrea Sacramento. So I also gathered some words from collaborators in this area. Of course, we couldn't miss some words from Carmen Romero Fuster. The best memory of my time in São Carlos was the opportunity to collaborate with Cidinha. I remember her enthusiasm for research, her tireless curiosity, and dedication to those of us who worked with her. I will always miss her wise advice. Farid, also, I took this from a talk he gave about Cidinha too. She was generous, determined, visionary, welcoming, supportive, and knew the importance of human connections. And even Suichi sent me some words too. Some years ago, in 2010, I had been asked by Cidinha to give some problems for the thesis of Marcelo Bossi. Then I recommended to read the book written by Cecil and Rian, and I started a collaboration with Cidinha and Marcelo on horror-tight submanifolds in hyperbolic space. Ana Claudia sent some very nice words. Cidinha was the kind of person who radiated joy in everything she did. One of my fondest memories is of her enthusiastically practicing her choir songs during breaks from our research work as we walked together to the restroom. It was a simple moment, yet it perfectly reflected her vibrant spirit, enthusiasm, and energy. For example, the music by Dindi by Tom Jobin. And Pedro also sent me some words. Cidinha was a brilliant mathematician, an inspiring mentor, and a dear friend to many. Beyond her outstanding contributions to singularity theory, she had a remarkable gift for bringing people together. In a community devoted to studying singularities, in a community, Cidinha was a force of unity. With kindness, generosity, elegance, and an ever-present sense of humor, she built connections, fostered collaborations, and made everyone feel welcome. Her mathematics will endure, and so will the warmth and joy she brought to our community. Okay, so we turn to the third topic, which is Bifurcation geometry. So Bifurcation equivalence lies in between analytic equivalence and topological equivalence. And inspired by Enria Panusinski, they found Bifurcation family which had moduli and non-trivial. I think it should be non-simple there. Anyways, a family with moduli. And so she got her student, Alexandre Fernandez, to work on this topic. And they defined strongly Bifurcation equivalence or families, strongly Bifurcation equivalence of families. And they studied the degree of Bifurcation determinacy of quasi-homogeneous function terms. And also with Alexandre, in the case of n equals 2, they showed something counterintuitive, which is that in some cases, in the quasi-homogeneous, if the functions are quasi-homogeneous, Bifurcation equivalence can imply analytic equivalence. And this is, Alexandre used to say that he didn't expect something like this, and especially with the techniques they used. But Cidinha had a very special insight, and she had intuition. She had intuition, and she said, no, I'm sure this, if they are quasi-homogeneous, this rigidity result is going to happen. And so they proved it in these two papers over here. And then also with another PhD student, with João Carlos Costa, in this thesis, they showed that there are only finitely many equivalence classes of polynomial function germs of degree less than or equal to k, up to k Bi-Lipschitz equivalence. So again, results without the restrictions taken now to the Bi-Lipschitz setting. Here there were some papers, first with Lev Vibrair and Alexandre Fernandez, and also with Takashi Nishimura. And very recently, she was studying with Sourav Trivedi the problem of density of stable Bi-Lipschitz maps. As I said, she was an expert in nice dimensions and things like this. So she was trying to understand this, but in the Bi-Lipschitz setting. And for this, they studied Bi-Lipschitz invariants of contact orbits in the boundary of the nice dimensions. And also related to this, they studied Bi-Lipschitz simplicity of function germs. So in those two papers with Sourav, the second one together also with the postdoc Nyan Nguyen. More recently, with Leonardo Camara, they studied the number of Bi-Lipschitz classes in families of quasi-homogeneous functions with constant Henry-Parusinski invariant. In this paper I mentioned of Henry and Parusinski, they defined an invariant. So here they said, okay, if the Henry-Parusinski invariant is constant, how many Bi-Lipschitz classes can there be for quasi-homogeneous functions? And with me again, we studied also the rigidity problem. That is, when quasi-homogeneous germs, function germs, but defined on a singular variety, when Bi-Lipschitz equivalence implies analytic equivalence. So we have this one of this preprint over here. And also in the Bi-Lipschitz setting, they studied the LNE problem in the space of matrices, together with Dimitri Kerner and Helge Moller-Pedersen. Of course, here there are intersections with other subjects, because this is also determinantal singularities, but well, of course, there are always intersections. So comments from collaborators in this subject. Alexandre sent some words. Cidinha had a rare combination of intellectual generosity, academic freedom, and fearlessness in the face of mathematics. For her, a problem never meant an insurmountable barrier. In front of classical or difficult problems, her attitude was of that who approaches with curiosity, confidence, and strategy, like a grandmaster of chess in front of an open game. Okay, so this was my contribution now, please.
And Cidinha also worked with determinantal singularities. In this topic, she had two PhD students. One of them was Miriam Pereira. And in Miriam Pereira's thesis, they first generalized the singularity theory of N by P matrices, based on previous work for square matrices, and also for N by N plus 1 matrices. Those work that they generalized was due to Tarde and Bruce, and also by Anna Frubs-Gruger. Second, they focus on variety with an isolated singularity at the origin, proving the existence and the uniqueness of smoothings to define their Milnor number. And finally, for surfaces in C4, they established a Legros formula linking the Milnor number to the second polar multiplicity, which is, in this case, the top polar multiplicity, and the Milnor number of a generic section. From Miriam's thesis, they published this paper. The other student in this topic was Nancy Chachapoya-Siesken, which was co-supervised by Professor Jean-Paul Bracelet. And they studied the Euler obstruction of EIDS that Ellen told it to us in her lecture yesterday. Choose nothing. They obtained some formulas to calculate the Euler obstruction for determinant variety, with whose the singular set is ISIS. And from Nancy's thesis, they publish this paper. Okay. She also published. She also worked with other people in determinantal singularity, and they published this paper. The first one with Nivaldo Gruglia and Gaffney. It is about Euler obstruction and characteristic classes of this class of variety. The second one with Inham Ahmed is about the singularity theory of the matrices and determinantal variety. The third one, again with Gaffney, it is about conditions to study Whitney singularity of families of determinantal variety. And the last one, it is about Nash blow-up of two generic determinantal variety. And this was nicely presented by Daniel in his talk. This was yesterday. She also worked in this topic with other people. And just because there are no joint papers, it does not mean that wasn't discussed mathematically or even created. And in this topic, she also had a lot of discussions and worked a lot with Juan Nuno Ballesteros, Bruno Ref Sokamoto, Ana Frubs Gruger, Matthias Zack, James Damon, Aaron Simmons, João Tomazella, and the others, right? And here, I got some comments of Aaron Simmons. Today, I honor a mathematician of incredible strength and sophistication, Professor Cidinha, who overcame physical hindrances to master the complex field of singularities. During my year at ICMC, her work inspired me to lecture on determinantal ideas, a topic that later shaped my lectures in Italy and became a textbook. Cidinha was deeply engaged from day one, constantly challenging me with profound questions. Behind her academic brilliance, she and her family showed immense warmth and hospitality to me, to my wife and me. We miss her dearly. Looking at the audience now, I can almost see her raising her finger to ask another one of her family's difficult question, for which I certainly wouldn't have the answer. Another topic that she also worked was topology of singularities. And in this area, she also had two PhD students. One of them was Raimundo Santos. And in his thesis, they investigated the Milnor vibration for real isolated singularities defined by map germs from Rn to R2. The main result connects the existence of this vibration to the C regularity of a family of hypersurfaces obtained by projecting F onto lines through the origin in R2. Additionally, the work explores family of analytic function germs to establish sufficient condition for both their topological triviality and the equivalence of their associated Milnor vibrations. And from Raimundo thesis, they published this paper. The other student, PhD student in this topic was Nivaldo Grulli. And in his thesis, which was co-supervised with Professor Jean-Paul Bracelet, they established relationship between the Bruce Roberts Milnor number and the Euler obstruction of an analytic function with an isolated singularity on singular spaces. Additionally, the work generalizes the local Euler obstruction to analytic maps on equidimensional varieties and provides a formula to compute the local Euler obstruction of K-frames using the local Euler obstruction of F. And one very nice thing of this thesis is that this was the first cotutela thesis here at the ICMC. After we had the others, but this Nivaldo thesis was the first. And from his thesis, they published with Jean-Paul Bracelet this paper. And then here we have another very special collaboration, which was the collaboration with Christoph Eyro. And now I collaborated again with the Polish School in Topology of Singularities, now through Christoph Eyro. They studied topological triviality of Zariski multiplicity conjecture for weighted homogeneous hypersurfaces. They publish together, they publish these three very nice works. And another thing that for me, I think that it is really nice of this strong collaboration that they had is that the Polish group, they have this weekly seminar, GKLW seminar in singularity theory that they organize. And because of this, well, in my opinion, it is because of this very strong collaboration, all semester they have a special session with the Brazilian mathematicians. So all semesters they invite 3 or 4 Brazilian mathematicians, and they organize this special session. She also published these other 2 papers in this area. The first one, it is a very important paper with José Sead and Verjovsky. This one, it's also a very interesting paper, and it is recent with Bárbara Lima Pereira and Ellen Santana. We have here some comments from Christoph Eyro. Working with Cidinha was always a pleasure. Her deeply mathematical insight, her clarity, and her generosity as a collaborator made every project both stimulating and joyful. I learned a great deal from her, and I remain deeply grateful for the years we spent working together. We also have these really nice words from Osamu Saeki. In 1993, I stayed for 2 months in São Carlos, and during that period, I met Célia, my future wife at that time. I had to return to Japan after the stay, but then Cidinha kindly applied and got a CNPq grant to support my stay in São Carlos in 1994. She is, in this sense, our greatest benefactor. Since then, she has helped us in many ways, always encouraging me academically as well. I am attaching a photo when I left São Carlos in 1995. We sincerely hope that she continues to watch over us warmly from heaven. And now, she also worked with bifurcation theory, dynamical system, and real algebraic geometry. On Monday, we saw the lecture of Isabel. We have here these two works. We know now that there is a third one in progress. And these two works, they are from bifurcation theory, and they also have applications, right? In fact, they are from mappings with applications in bifurcation theory, right? These two are from dynamical system, and the last one is on real algebraic geometry. Márcio Soares also sent some words. I met Cidinha in 1982 at the ICMC event, where our immediate mutual empathy is sparking a lifelong connection. Despite the limitations of communication at that time, we maintained close contact. I had the privilege of following her entire academic trajectory, serving on her PhD, habilitation, and through professor committees. These years proved to me that Cidinha was an exceptional mathematician, an outstanding mentor, and a vital leader in Brazilian mathematical community. Having shared many events and committees with her worldwide, I was always deeply impressed by her serenity. Her memory remains unforgivable, and high charity. Regiane Oliveira also sent me very, very nice words. I feel that I will never be able to thank her enough for everything I received from her. Her absence is still difficult to accept. Many times it feels as I thought I might meet her again at any moment in the hallways, with her kindness, her thoughtfulness, and her careful chosen words. I also carry the feeling that I could have made better use of the time we shared, learned more from her, and enjoyed more opportunities to be in her company. Yet, above all, what remains is a profound sense of gratitude. I had the privilege of knowing Professor Cidinha, of receiving her support and trust, and I will carry her example with me always. And the last one, it is a very special for me, because Miriam Manuel was the driving force of this edition of the workshop, and she also sent very nice words. Cidinha played a decisive role in my development as a researcher. At the end of my master's degree, when I was still taking my first steps in mathematics, she provided me with an opportunity that changed the course of my career. She put me in a seminar room with Mart Golubitsky so I could present my master's results and discuss my interest in pursuing a PhD applying singularity theory to dynamical systems with symmetry. It was an enormous gesture of trust that opened doors and made me feel for the very first time part of the international mathematical community. Cidinha had this rare ability to truly see people and create opportunities for them to grow. Much of what I built afterward was born from the conversation and from that conversation and her generosity in betting on me. And it is this. And I think that we all agree that Cidinha's existence was a singularity in the best sense of the word, a unique combination of mathematical brilliance, humility, and kindness. And that's it, right? Oh. Okay.
Okay, so thank you very much for this comprehensive and emotive talk about Cidinha's legacy. So I don't know if someone here want to add something or comment or no. So I think this night we. So Isabel, no.
Okay, just a sort of funny comment. You should add me to the list of Cidinha's postdocs. Because 1 year I was coming here on sabbatical, and Cidinha was trying to get financial support for my coming. So she said, would you mind being a postdoc? I said, great. No, I had a grant from PAPESP to be a postdoc of Cidinha. But before I said yes, I went to check that she had done her doctorate before me. 1 year.
Okay, of course, we have to say we are sorry if we missed any one of you. This was a very difficult task, and we might have missed some collaborations on paper, but I hope we gave a good idea of everything she did and everyone she worked with, which was our goal. Yeah.
So anything else? Okay, so I think this night we will have.
Of course.
Yes, of course.
Well, I cannot say thank you. It's not for me. But what I can say is that she would love to be here talking mathematics with you. That's all. Thank you.
Okay, so this night we will have a drink in honor to Cidinha again.
Sí, ahora es lo que no sabía si Fer es de matemático.